Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the Module 2 question from the Cape Chemistry Unit 1 Paper 2 from June 2024. So this is question 2, and 2 part A says, what is meant by dynamic equilibrium? So dynamic equilibrium refers to the state in a closed system where molecules of reactants are continually being converted to products and molecules of products are continually being converted into reactants, right? So there's a constant back and forth of reactants to products, products to reactants. In this state, right, so in that state of dynamic equilibrium, the rate of the forward and backward reactions are equal, and the concentration of the reactants and products remain constant, right? So this is the all-encompassing definition of dynamic equilibrium. If you state all of these things, you will for sure be given the 2 marks, okay? So just make sure that you capture all of these things when we talk about dynamic equilibrium. So let's go ahead now to part B. Part B says that the reaction between A and B to form C and D is represented in the following equation. So here's an equation. We have A plus B being in equilibrium with the products C plus D, right? The equilibrium constant value for the reaction is 4.0. All right. So let's see what the question is asking now. The question says in part 1, write an expression for the equilibrium constant of the reverse reaction. So an expression for the equilibrium constant for the reverse reaction, right? So in every equilibrium, you know, there are 2 reactions, right? You have a forward reaction, which is this one, going in the forward direction. So that would be your forward. And then you have a reverse reaction, which is coming back this way, right? When you're going from products to those reactants over there. So we're being asked to write an expression for the equilibrium constant for the reverse reaction, right? So the equilibrium constant in general, when we're writing an equilibrium constant expression, we're always gonna write what? The products of that reaction, the concentration of the product is gonna be on top, right? And then the products of the reactants will be on the bottom, right? So here's what we come up with. Remember now, we're looking at the reverse reaction, so we're looking at the reaction that is going this way, right? So when we look at that, our products would be the A and the B. So we have those on top, their concentrations, the product of their concentrations. I'm going to divide that by the product of the concentrations of the reactants. In this case, our reactants are C and D because it's the reverse reaction. And so that is our expression. All right, done, done, done. 1 mark. All right. State the numerical value of the equilibrium constant for the reverse reaction based on the expression in B part 1. So here's the expression that we wrote, right? Earlier on up here, we were told that the equilibrium constant for the reaction, aka the forward one, is 4.0, right? So the forward reaction has an equilibrium constant value of 4.0. So let's just do something here real quick. Let us write the equilibrium constant expression for the forward reaction as well. So I'm going to write K forward would be equal to what? These are my products of the forward. So it would be C, D over A, B. So that's the forward, the expression for the forward reaction, and the value for the equilibrium constant, this guy Kf, is 4.0, right? So that's all given to us here. So if we're to state the numerical value of the equilibrium constant for the reverse reaction, aka this one, Kr, when we look at Kr, right, the expression for Kr, and we look at the expression for KF, what do we see? Right, we see that it's literally just a reciprocal, right? It's 1 over. You see that? If I compare the AB over CD to CD over AB, it's just that they're 1 over. Like, that's the difference. They're related by a reciprocal. So if I were to flip this, I would get this. So all I have to do to find numerical value is just say 1 over KF. 1 over KF is equal to KR, right? And so then that would be 1 over 4.0 is equal to 0.25. Okay, so that is the numerical value. It's just a reciprocal of the forward. Okay? All right. So let's go ahead now. So 2 part C says state Le Chatelier's principle. So Le Chatelier's principle states that if one or more factors that affect an equilibrium are changed, the position of equilibrium shifts in the direction which opposes the change. Okay? All right. So that's Le Chatelier's principle for 2 marks. So part D now says consider the following equilibrium reactions, right? So let's look at equilibrium A. We have steam and carbon solid being in equilibrium with a mole of H2 gas and carbon monoxide gas. And we see that it has a delta H, or an enthalpy change, or enthalpy of reaction of positive 131 kilojoule per mole. So that means that this is a, let me just jot it there, that this is a endothermic process because it's a positive delta H, okay? And in equilibrium B, now we have 2 moles of these CrO4 minus ions reacting with 2 moles of H plus ions, and then that's equilibrated to give Cr2O72 minus aqueous and liquid water. Right, so those are the 2 equilibrium reactions that we're concerned about here. Okay, so let's go ahead now. So now we're being asked to use Le Chatelier's principle to predict and explain the effect of increasing the pressure on equilibrium A. Right, so let's look at equilibrium A again. Let's bring our focus to this equilibrium A. Increasing the pressure on equilibrium A. Right? So when we think about increasing the pressure, when we think about doing anything to a pressure, what we have to immediately think about is, okay, when I look at my equilibrium, I have to see which side, right? Which side of the reaction, is it the reactant side or the product side that has more gas molecules, right? Or fewer gas molecules, or so more generally, do both sides of my equation have the same number of gas molecules? If not, when you change the pressure, something is gonna happen. Okay? Now figuring out what's gonna happen is where it gets interesting. So if I'm increasing the pressure on equilibrium A, what does that mean? That means that there will be a lot more collisions taking place, a lot more gas particles are squished in a small area, right? And so if I need to relieve that pressure, per Le Chatelier's principle, it says that, you know, the system will try to oppose that change or relieve that pressure, then the equilibrium will want to shift in the position on the side of the equilibrium where there are fewer molecules to relieve that pressure, where there are fewer gas molecules. So when we look at this, we see that there are 1 mole of gas molecules over here, and there are 2 over here, right? So see, 2 moles of gas molecules over here, and then it's just 1 mole, which is the steam. So the equilibrium is going to want to shift to the left to relieve that pressure that we increased on that system. Okay, so that's what we would say here, right? Increasing the pressure shifts the position of the equilibrium to the side of the reaction where there are fewer gas molecules. That's the left. So equilibrium position will shift to the left. All right, so let's go ahead now. We need to say, okay, what's gonna happen if we decrease the temperature on equilibrium A? Decreasing the temperature on equilibrium A, what is that gonna do to the equilibrium position? What's gonna happen from Le Chatelier's principle, right? So as we said earlier, very, very important thing to note here is that this forward reaction, so as written, right? The forward reaction is endothermic, right? So if the reaction goes in this direction, which is generally as written, it will go in that forward direction. It's endothermic. It means that it absorbs heat. Going in that first direction is a process where it absorbs heat. It takes up heat, right? And so if it is that we're at equilibrium, nice, everything is steady, right? And you drop the temperature, you decrease the temperature on equilibrium A, right? So you've disturbed the equilibrium by dropping the temperature. What's gonna happen? The system, right, is gonna want to move in such a way to bring back up the temperature, right? So it has to move in a direction where heat is given off, which is the reverse direction. The reverse direction is exothermic, right? And how do we know that? If the forward direction is endothermic, the reverse direction is exothermic. And so if we drop the temperature of the system, then the system is going to be like, oh no, we need to get back to where we were. We need to move in such a way that we can give off heat so we can come back up to our equilibrium state. And to do that, it will shift to the left or to the reactant side, the reverse direction, where it is exothermic. Okay? So in a nutshell, decreasing the temperature of an endothermic reaction results in the position of the equilibrium shifting to the reverse direction in which the equilibrium is exothermic, as this will liberate heat to oppose the change that it was imposed upon it. Equilibrium position will shift to the left in the exothermic direction. Okay, so let's go ahead now. Finally, if we increase the H plus concentration on equilibrium B, so now we're zeroing on equilibrium B. And we're saying, okay, if we increase this, so if we like dump in a bunch more H plus ions, right? How is that gonna affect the equilibrium based on the Chatelier's principle, right? How do we explain what's gonna happen there? So here's how we explain this one. Increase in H plus concentration results in the position of the equilibrium shifting in such a way to use up the extra H plus ions that are now present in the system, right? So the equilibrium position will shift to the right. It will shift to the right. Why? Because now it needs to use up the excess H plus. And which process uses that up is when it goes to the right to make more of the Cr2O7, 2 minus, and water. So the equilibrium will shift to the right to use up that, to minimize that excess that's there, okay? All right, so that's our answer there. So let's go ahead now. So part E says a buffer solution containing 0.2 mole per dm cube of a weak acid, HA, and 0.5 mole per dm cube sodium salt of the weak acid, Na, was prepared for use in the food industry. Define the term buffer solution, right? So a buffer solution is a solution which minimizes changes in pH when small amounts of acids or alkalis are added to it. Okay, that's our buffer. That's our all-encompassing definition. It's going to minimize change in pH if we had a small amount of acid or alkali to it. All right. Given that Ka for the weak acid is 7.4 times 10 to the minus 4 mole per dm cube, calculate the pH of the buffer solution. So now we're calculating pH of a buffer solution. The strategy that we're going to use is that we're going to use the Henderson-Hasselbalch equation. That is your master equation whenever you're calculating pHs of a buffer solution. Okay, so here's that equation here. It says that the pH is equal to pKa plus log to the base 10 of the salt concentration divided by the acid concentration. So it's a ratio, right? It's a log 10 of the ratio of the salt concentration to the acid concentration. All right? And so if we need to find pH, this is our unknown, right? pH is our unknown in this whole thing. So we know pKa. Here's how we're going to find the pKa. We know Ka, so automatically we know pKa. pKa is equal to the negative log of the Ka, and so we're going to do negative log to the base 10 of 7.4 times 10 to the minus 4, and that gets us a value, a pKa value of 3.1308, right? So we have this first part, nice, and so now we have the salt concentration that we were given from up here, it's 0.5. So that's what we're going to put here in our salt, right? And then we also have the acid concentration, which is 0.2. And that's what we're going to put here to round out this calculation. So here it is. So the pH is going to be equal to the first part that we just got, which is the pKa, 3.1308 plus log to the base 10 of 0.5, which is our salt concentration, divided by our acid concentration. We plug everything through. We get a pH value of 3.5287. Okay? All right. So that is the pH of this buffer solution. Okay? So let's go ahead now. Outline the experimental procedure that can be used to prepare a sample of the buffer solution in E. Include in your answer tests to be used to ensure that a buffer solution was in fact made, right? So here are some steps. All right, so this is to prepare a sample. So let's just imagine that we're preparing a 250 centimeter cube sample of the buffer solution. So a pretty small volume, fairly small volume. We're going to need to measure out, first of all, the 250 cm cube of a 0.2 mole per dm cube solution of the weak acid. So let's imagine that we just have this in our lab. We have the solution of the weak acid in our lab at this concentration. We're going to take out 250 cm cube of it. Then we're going to weigh out the required mass of NaA to make the 0.25 mole dm cube solution of NaA that we need. Because remember earlier, what our buffer solution was comprised of. The weak acid would have been HA, right? And then that would have been in equilibrium with the salt, right? This is the salt or the conjugate base. And then, of course, you know, H plus, right? So that's generally how the equilibrium works. So this would have been our acid, and then we would have added in the conjugate base, or the salt is what we call it. So that's how we make it. We're literally taking the two things and adding them together. So in the first step, I've taken the weak acid, and then in the second step, I'm weighing out how much of this salt do I need to put in that 250 cm cube to make it that concentration, because these are the concentrations that we're working with from part E, right? So then after I weigh out the required mass, then I'm going to dissolve that in the 250 cm cube of the solution from step 1 and just mix it well. At that point, I've made my buffer solution. I just mix. So what I'm going to do then is I'm going to place a glass pH electrode into the buffer solution that we just made, and then read off the value of the pH on the pH meter. Then I'll know at this point, I will get what the pH of my buffer solution is, and I'll see if that in fact matches what we just calculated earlier, which was, what was that? 3.5, right? Around there about. So we'll get the pH of the buffer solution here when we dip this glass electrode into the solution. All right. Here are our tests now. These are our two tests that we're going to do to see if it's functioning as a buffer, right? So we're going to take a small aliquot of the buffer solution that we just made. So like maybe, let's say we take 50 cm cube, right? Just for argument's sake. So we take 50 cm cube out of the 250 cm cube. And then we're going to add like a teeny tiny amount of NaOH to it, right? Then we're going to record the pH. When I record the pH, ideally, the pH will still be in the neighborhood of what I'd gotten, right? Remember earlier we had gotten 3.5-ish thereabout for our pH. When I add a small amount of NaOH to my little aliquot of the buffer solution, it doesn't really change much. It's still in the same general area. Then I know, oh, it's buffering, right? It's working, it's minimizing changes in the pH. And then similarly, here's another test now. if I take another small aliquot, so another 50 cm cube, just a little small portion I take out of my larger 250 cm cube, and I add a teeny tiny amount of HCl to it, right? Mix, 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 and I record the pH. When I record the pH, I see that it's still around 3.5. That means that my buffer is working. I did in fact make a buffer solution. If when you do these little small aliquots and add in these NaOH and this HCl, and you see the pH changing dramatically, so say the pH jump to all 4.5, jump down to 2.5, then you know that your buffer, you didn't make a buffer solution, okay? Something needs to be changed, something would need to tweak for that to do its job as a buffer. But if when you add these small amounts of alkalis or acid independently, and you see that the pH is pretty much wherever it was from before when you made the buffer, then you succeeded in making a buffer solution. Okay, so let's go ahead now, clear this. So 2-part G says, with the aid of equations, explain how a solution of ammonium sulfate and ammonia can control pH, right? So just a while ago, when we spoke about how we would make a buffer solution in the lab, we kind of highlighted the two key pieces or two key elements that you need whenever you're making a buffer solution, and they've kind of given us them here, the two elements, right? We have our ammonia, which in this particular instant will function as a weak base. And then the ammonium sulfate, you know, that's a salt, right? So that would be a salt / our conjugate acid, okay? Conjugate acid. So we have our two key elements that we need here. And so from an equation standpoint, right? When we make this buffer solution, we're adding ammonia and the salt together. And so the equilibrium that we get set up then in that buffer solution will be this right here. So we have our weak base, and that's equilibrated with the conjugate acid here. The H+ ion is here. And something I want to point out here is that this is just like a net ionic equation, right? We know it's ammonium sulfate, but ultimately in the grand scheme of things, it's gonna come down to just the ammonium ion, right, doing its function, and the ammonia itself. So we don't need to show the sulfate per se being present, okay? At the end of the day, this is the equilibrium that gets established when we make our buffer. So this is our starting point. For any explanation that we're gonna do as to how this functions as a buffer, this is our equilibrium. This is our starting point. So let me just write that beside that this is our equilibrium state, right? That is our equilibrium state, right? And the key idea here, before we even get into any further explanation, is that when we were looking at the Anderson-Hasselbalch equation earlier, remember we had a ratio of salt to acid, right? And so as long as that ratio more or less remains constant, then you're not going to change. The pH is not going to change, okay? So remember, this is the Henderson-Hasselbalch equation, pKa plus log to the base 10 of all of this. So what we're saying is that as long as this ratio doesn't really change much, then your pH is gonna remain more or less constant, right? That's the big premise behind these buffers. So let's go ahead now. This is our equilibrium state. This is the setup. If now, I'm explaining how it works as a buffer now. If it is that I add a small amount of acid or H+ ions, here's what's gonna happen. The weak base, right? Remember now what bases are. A base is a what? Acceptor of proton. The weak base is gonna absorb those protons or the acid that I just added to it, and then it's gonna end up forming more of the ammonium ion, okay? So that equilibrium then is gonna shift to the right, okay? The equilibrium will shift to the right. because I just added some H plus in, and in order to maintain the system, it's gonna have to go shift to the right to use up the H plus that I put in. Okay, so the equilibrium shifts to the right. And so in so doing, it maintains that balance there, okay, of salt and acid that's present. Okay. So now, upon the addition of small amounts of base or OH minus ion, so to think about that now, remember, this is our equilibrium state, right? This is our equilibrium state up here. If we're adding in base or OH minus ions, what exactly are we doing, right? If I'm adding in OH minus ions, what's gonna happen? Remember now, bases, they're acceptor of protons, right? So what is it gonna do? It's gonna deplete out the H plus. So the H plus concentration is gonna drop, and so the equilibrium is gonna have to shift to the left. Okay? And so from an equation standpoint, we can write it like this. You have your ammonium ion, right? And that ammonium ion, right, that's a conjugate acid. So it sees this base. The base is an acceptor of proton. It's gonna snatch off a proton off of the NH4 plus. It's gonna become, the NH4 plus is now gonna become ammonia, and water is gonna form because the H from the ammonium ion and the OH goes together to form water. Okay? So there are really two ways that you can explain how buffers work generally, right? You can use the Chatelier's principle, or you can just use a direct acid-base reaction to explain it. And I've done both in this case here, okay? So just keep that in mind. So in this case, then, if we're depleting NH4 plus, right? If the NH4 plus is being taken up with the base, then the equilibrium is gonna shift to the left, okay? All right, the equilibrium shifts to the left. So part H says define the term half-life. So the half-life of a reactant is the time taken for the concentration of a reactant to fall to half of its initial value. Okay? I says using a Boltzmann distribution curve, show how a catalyst affects the rate of a chemical reaction. Okay? So here we are, the effect of catalyst on the rate of a reaction. Whenever we draw any Boltzmann distribution curve, on our y-axis, we're gonna have the fraction of particles with a particular energy E, and then on the x-axis, we're gonna have the energy E, right? This is the general shape of a Boltzmann distribution curve, right? And the area under the curve represents the fraction of particles that have a particular energy, right? And so when there is no catalyst, so when it's uncatalyzed, you see that the area under the curve, so this white area, is much, much smaller than when you add a catalyst. You see that there are more. So now you have this blue part that gets added on to this, right? So there are more particles that exceed the activation energy because the activation energy is lowered, right? All right, so the presence of a catalyst provides a reaction pathway with lower activation energy so that more reactant molecules are able to equal or exceed the activation energy. All right, so remember now, when it's uncatalyzed, this is the activation energy, and only these particles exceed it. When it's catalyzed now, you have a lower, even lower activation energy, so more particles can exceed it. Okay? And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on the left here, you'll see the next video up. And if you look on the right here, you'll find our Module 2 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So, thanks for watching, and we'll see you in our next video.